100 million volts of energy, of kinetic energy is going to come out, so that you'll have these two fragments coming out with tremendous speed, which you could convert into heat, for example. And then her nephew Frisch went back to England, where he was hiding, and he actually detected them using a cloud chamber like we saw. He put the uranium here, he shot neutrons at it, and he saw the fragments coming out into the cloud chamber, very high energy fragments coming out. They put in low energy neutrons, and all of a sudden, poof, you get two big fat fragments coming out with high speed. And he proved visually that the uranium was splitting into two pieces and coming out with high energy. And then people around the world here at Berkeley went crazy. They just searched for this and reproduced the results and carried it on further. So it's a very exciting story, as you know, and the implications were earth-shaking, literally. So we started our discussion with more or less how to describe nuclei. Remember that we just give the number of protons by the letter Z, number of neutrons by N, that sounds better. A is the mass number, which would be the sum of these two. And then we have the fact that you have the possibility of having one chemical element, like uranium, which can have 92, let's see, I'm not sure exactly how to do this, with 235 particles altogether. This would be your A number, this would be your Z number, and your N number would be A minus Z. So let's just see how many neutrons that is. It's 235 minus 92. So you have 143 neutrons. So what you'll notice is that there are more neutrons as you go up in the periodic chart. The number of neutrons compared to the number of protons tends to increase. For example, we have a case, a very stable element, helium, which is, like in this notation, 2 and 4. So you have Z equals 2, N equals 2, and the total number is 4. That's typical. In the lighter elements, you sort of have about the same number of protons, neutrons. Carbon, I think, is the typical carbon is element 6. 6, maybe put 6 here, and it's 12 is the usual atomic weight. So again, you have 6 protons, 6 neutrons, and a total 12. Although carbon has isotopes, there's a carbon 13, a carbon 14, which has extra neutrons. This one is the stable one. When you get the carbon 12, it lasts forever. The higher ones tend to be radioactive and change into carbon 12. Okay, so that's the gist of this. I did mention to you many times, and we talked about the fact that you do nuclear magnetic resonance on the magnetic moment of the nucleus. Typically, if you work with the nucleus of helium, hydrogen rather. Hydrogen has its magnetic moment. It has angular momentum, spin a half h bar, and because it's spinning, it's a plus charge spinning, that represents a magnetic moment. And this precession that you see, the wobbling, if you can get a resonance field to do that, you can get this magnetic moment to pick up energy, and that's nuclear magnetic resonance when you get into step with that frequency. So that is something that you do in your lab. I'm sure you will in chemistry sometime. And of course, that's a very big field too now with MRI. Then we have this idea of radioactivity discovered by Becquerel, and the Curies found a bunch of other things, polonium, radium. Polonium is interesting. They just found that, in the news about polonium, the Palestinians said that Yasser Arafat was poisoned by polonium, because apparently it's very deadly stuff. There was some Russian spy or something who was poisoned by polonium in London, and there was a big scandal about that. But polonium is pretty dangerous stuff. Polonium was discovered by Curie, Madame Curie, and she named it after Poland, her home country. But apparently it's not good to have in your body, even in small amounts. Radium and a couple other things, and that's one of the reasons she won the Nobel Prize. But the point is that we have the typical radiation, so this is not a complete list, coming out of the nuclei. If we did our Wilson cloud, the cloud chamber thing, if you put a magnetic field over the radiation, if you had a magnetic field, say, going into the blackboard, say, what happens is that the charges, what you find is there's some radiation that goes straight. Some of it bends this way, and some of it bends this way. So from this, you're supposed to be able to tell what kind of charge it is. So let's see if we can remember from earlier in the course what it is. Suppose that you have a curved orbit like this. So let's, can we say whether this is a plus charge or a minus charge? Let's see. Recall. Suppose, let's imagine it's a plus charge, and it's a current going in this direction, I, and then cross B. The force would be in this direction if this were a plus charge moving in that direction. Right. So this I guess, right, this would be a plus charge because it's curving this way in the magnetic field. On the other hand, let's say, so almost obviously this has got to be a negative charge because it curved the other way. In other words, it represents a current going this way, and you turn it toward the magnetic field. Remember, the force is equal to QV cross B. Well, it depends on the sign of the charge. So if the velocity is this way, but the charge is negative, the current is this way, and or okay, let's have V cross B would be that way, but with a negative charge, the force is actually that way on a negative charge. So this one would be negative. In fact, with the way the radiations look, this one has a large arc, and these ones bending the other way tend to have small arcs like that because they're lighter. So the force bends them more. So we would call these our electrons, and these are heavy particles, alphas, it turns out, which are helium, ionized. It's massive. It has 4 nuclear particles, and this is a light electron. So when you have a radioactive source and you put in a magnetic field, you'll see the helium's bending this way and the electrons curling up and bending that way. And so they sort out, and the one that goes straight ahead is not bent by a magnetic field, so we call that some kind of electromagnetic radiation, and we call that it's a gamma ray. Or, yeah, so this one, the alpha particle, the helium, is called alpha. Beta is this one, the negative electron, and gamma is the one that's electromagnetic radiation, goes straight ahead. So those are the principal ones. But in addition, as I think the book points out, that some nuclei in fact shoot out positive electrons, beta plus, and sometimes you'll even get what's called K capture. We'll talk about that. Again, this is a Fermi contact interaction where you have a nucleus, and because the electron is sitting, the s electrons, or the K, 1s or K electron is sitting more or less on, some of the time, right on the nucleus. Sometimes the nucleus will capture that negative electron, and we call that K capture. So that's another possible reaction. Oh, you should know about this, actually. There's a medical treatment called positron emission tomography. Have you heard about that? Positron. That's the E+ thing. Yeah, well, you should mention that clearly. Yeah. So in addition to some nuclei, not only shoot out negative electrons, they'll shoot out positive electrons. So that, in fact, you would get a positron would bend around in that way. See, because it's light, it's an electron, but it would bend this way. So you can get beta+, which is called a positive electron, positron. And this is used for imaging of certain medical problems. So you have positron PET scans, right? Positron emission tomography, which is the beta+ particle, a positron being emitted. I guess you do the because it's such a special thing to have a positron emitter that if you ingest something like that, if you see beta+ particles coming out, you're pretty sure it's because you put it in there. You're familiar with these terms, positron emission tomography. You know what the word tomography comes from? Tom is the Greek word to cut. So you have a tomograph for cutting things. So this is a way of getting the sort of image in slices. The word atom, in fact, comes from that word. Atom means you cannot cut it. And the thought was the atom was the smallest possible thing, and you couldn't break it. We know now that you can. So we know we can cut atoms, we can get the electrons off, right? But it was thought that the atom was the elementary unit, which is unreduced, uncuttable. So it's atom. That's good, because you use the word tomograph a lot, don't you? I mean, don't you have a machine that cuts things in thin slices, tomographs? No? It used to be that you cut tissue into very thin slices. No? You use that word? I thought you did. Okay, well, you can now. It's your word. Okay, so we showed how you can detect these radiations because they ionize things. And when they ionize, they break the atom in the sense that they take the electrons off. They don't necessarily break the nucleus. That's a different story, which we'll get to, of course. Then we have the idea of radioactivity, that if you wait, this is Rutherford's experiment where he uses radioactivity as a source to send particles through the gold foil and sees that sometimes particles go through, most of them do, but every once in a while they bounce off a heavy nucleus, and sometimes they even rebound entirely. And he was able to, Rutherford did some classical theory on the repulsion of a positive charge against positive nuclei, and he predicted a curve like this, and that's exactly what he got for the number of particles that would bounce back, and the angle through which they would bounce. So he says, I have a nuclear atom. Then, of course, we have the idea of, if you have a radioactive material, it's decaying, and there's a certain lifetime to it. If you start out with a certain number, n sub 0, it dies out exponentially with a certain decay constant, lambda. The inverse of that decay constant is what's called the mean life. More often, things are described in terms of how long does it take for half of the sample to disappear. So then the formula becomes, I start out with a certain number, n0, and it's 2 to the minus t over what's called the half-life, which is the word you'll hear a lot in the discussions here. So that when t is equal to t1/2, you get 2 to the minus 1, which is 1/2. So in every interval of time equal to t1/2, the sample is 1/2 disintegrated. So that's why we call that t1/2 the half-life. And it's related to this decay constant, but almost nobody talks about the decay constant. It's always almost given in terms of the half-life, although they're very similar numbers. The decay constant, if you plot, I start out with a certain number n0, and I wait a certain amount of time, the number will go down. It'll go down to a half. That's n0 over 2 in a half-life. It'll go down to n0 over e to the minus 1, which is n0 over 2.7. It takes a little bit longer. It's the difference between 2 and 2.7. This is the tau, the mean life. So they aren't that much different, but somehow this is an easier number to work with. So you can say that every time I start with something in a half-life, I'll have half as many particles as I started with remaining. So that's just good to know. Well, the other things, we have just a few more minutes, but you want to know the rules of nuclear reactions. Typically, when we start out with a certain number, we end up with the same number. They just maybe separate, or you add things to it, and you keep the total number, unless they change. Sometimes if you emit a negative charge, it creates a neutron is going to a proton. See, a neutron, you can think of, it's not correct, but you could almost think of it as a proton plus an electron. So if you see an electron come out, there's a proton left behind. So, and if a proton is created in a way, then it increases the number of protons, namely Z, so it becomes a different chemical element. But of course, the number of neutrons decreases, but the total number has not changed. A is the same. You can think about that. I think it's pretty clear when you think about it. So it is a very interesting little cultural fact that neutrons and nuclei seem to last forever. In other words, not every atom decays, and not every neutron changes into a proton. Inside a nucleus, stuff will last, as far as we know, matter is stable to like 10 to the 34 years, something like that. Way beyond the life of the universe, we have stable matter. On the other hand, if a neutron comes out of the nucleus, it's unstable and it doesn't last. It lasts maybe 15 minutes. 15, what did I say, 8? I thought recently 8, yeah. Something like 8 minutes. And then it decays into a proton and an electron and another little particle. So when they're alone, it's maybe an argument against bachelorhood. When they're alone, they decay very fast. And when they're inside the nucleus, they seem to last forever. That's what happens if you're a neutron. The rest of us, I'm not so sure. But anyhow, so you do get nuclear reactions. Now, this is a very important one down here, where uranium, on the isotope 238, when it picks up a neutron, it goes through a whole series of reactions, which you can read here. If it emits a gamma ray, it doesn't change anything. Okay, but once it's at 239, because it picks up a neutron, it goes to 239, but the neutron doesn't change the number of protons. But then it emits a beta particle, which means a neutron has changed to a proton. If it changes to a proton, that means there's 93 protons where there were 92 before. So, but it's a new chemical element. This is the one that Fermi thought he had, 93, which we now call neptunium. Oh, you'll notice that it's named after the planets, uranium, neptunium, plutonium. Okay, so then the neptunium goes to plutonium by again emitting a beta particle. A neutron is changed to a proton, so you get one more proton, and this is now plutonium. And this plutonium is pretty stable, 24,000 years. And also it turns out that it's a fissionable material. So to talk about fission, the idea is simply that the most stable elements are the ones in the middle of the table around here. Iron is a very stable nucleus. If you can go from this to this, you can give up energy because things become sort of lower in the well and you give up energy. So if you can go from, say, hydrogen to helium, you go up the chart, you give off energy. Or if you go from uranium toward the middle, oops, I'm sorry. If you go from uranium toward iron, sort of toward the middle, you also give up energy. So that's the origin of our search for nuclear energy. Because if you can convert elements from uranium to something here or hydrogen to something here, you actually gain energy. Now fission comes about because, as I said here, this is the line for equal numbers of neutrons and protons in an element. And you see for light elements, they're pretty much equal numbers of neutrons and protons. This is the number of neutrons, and this is the number of protons. But as you go heavier, you have more neutrons than you have protons in the nuclei. So the point was, when they discovered that the elements were splitting from here to here, we speak of the element splitting, and you form what we call daughter nuclei. So you have your big uranium with 92, 235 total. It splits. What happens? A neutron comes in. It destabilizes this nucleus. And off come two pieces, which are light. Let me make them quite a bit smaller, which add up to this, more or less. But these daughter nuclei don't need as many neutrons because they're lower down. So in addition to these, what you get is some number of neutrons. The question was, how many? They realized that if you get enough neutrons, you'd be able to use those neutrons to hit another uranium element, and it would again have its daughters, and a couple of, what should we call them, orphan neutrons coming off here, not attached to anybody, and they could cause another reaction. So you could have a chain reaction whereby you use this to break it. So this is a model of the first atomic pile that Fermi built in December 2nd, 1942 was when they first did this. They had uranium, but they wanted slow neutrons. The neutrons were coming out of the uranium. They slowed them down in a graphite pile of blocks. Now they had to control how many neutrons they were because you don't want this reaction to go too fast. So in addition, they put in these control rods. They put them in, they were made of cadmium, which Fermi knew would stop the neutrons, slow them down, or absorb them. And then somebody started pulling the rods out to let the neutrons get across from one to the other and cause reaction to occur. And they kept monitoring how many neutrons were actually going and how fast the reaction was going. And finally, they reached the point of criticality where as many neutrons were being created as you need to keep the reaction going, and that's when you stop. Now, if you don't stop, well, here's another picture. What happens is when that splits, it doesn't actually split half and half. You get a whole variety of elements in here matched with another set of elements in here. And, okay, before everybody leaves, I want somebody might have some fun. You want to set off a chain reaction, anybody? Okay. Somebody, you want to volunteer? Come on. Yay, be the first on your block to set off a chain reaction. What we have here is mouse traps with two balls. Have you seen this? Two balls on all these mouse traps. We'll drop in one neutron, one ball, to do it. And if it hits one of the traps, two will come out. Those two can hit two more. Blah, 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 and you get the thing. Be my guest. Come here, so not that you get hurt. Watch carefully. That's it. Bravo. Nuclear man. Okay. Thank you. Very good. Oh, yeah, thank you.